Hello and welcome to Earthquake Tip number 18. My name is Shailesh Agrawal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to comprehend language to our professionals who are in the field designing and constructing buildings and structures, especially our engineers and architects. But before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. This earthquake tip number 18 will explain you how do beams in RCC buildings resist earthquakes. Remember, in the last tip, I told you that RCC building comprises of horizontal and vertical members, namely beams and columns. These members are built integrally with each other. Therefore, under the action of loads, the beams and columns act together as a frame, transferring forces from one to another. Through this step, we will learn how beams that are part of building frame carry earthquake-induced forces. Now let's look at this figure. Beams in RCC buildings have two sets of steel reinforcement. Long straight bars called longitudinal bars placed along its length. Closed loops of small diameter steel bars called stirrups or links placed vertically at regular intervals along the full length of beam. Always remember these stirrups play important role in resisting earthquake forces. Now let's see how beams sustain failure during earthquake through this figure number 2. There are two basic types of failure: flexure or bending failure, as shown here in this figure 2a. As the beam sags under increased loading, it can fail in two possible ways. If relatively more steel is provided on the tension face, in engineering parlance, it is called over-reinforced beam, concrete crushes in compaction, which is brittle failure, and therefore it is undesirable. However, if less steel is present on the tension face, called under-reinforced beams, the steel yields first, means it keeps elongating but does not snap. Remember earlier tip, steel being ductile material, it has ability to stretch large amounts before it snaps. This helps in redistribution of forces until eventually the concrete crushes in compaction. This is called ductile failure and hence desirable in earthquake resistant design of beams. So remember, more steel on tension face is not necessarily desirable. As you can see in this figure 2a, the ductile failure is characterized by many vertical cracks starting from stretched beam face and going towards its mid depth. Now let's see this figure 2b. This shows shear failure. A beam may also fail due to shearing action. A shear crack is inclined at 45 degrees to the horizontal as shown here, and it develops at mid depth near the support and grows towards the top and bottom faces. Closed loop stirrups, as shown in earlier figure, are provided to avoid such shearing action. Shear damage occurs when area of these stirrups is insufficient, means their spacing and diameter. Shear failure being brittle must be avoided in earthquake resistant design of RCC beams. Now let's discuss the design strategy of RCC beams. Designing of beams mean selection of its material properties, that is grade of steel bars and concrete, its size and shape. These are usually selected as a part of overall design strategy of the whole building. Next is the amount and distribution of steel to be provided in the beam. It is determined by performing design calculations as per concrete design code, that is IS 456, and ductile design code, that is IS 13920. Now let's look at this figure 3. Longitudinal bars in beams are provided to resist flexure cracking on the side of beam that stretches. As explained you in earlier tip, during strong earthquake shaking, both top and bottom faces of beam stretch. So longitudinal bars are required on both the faces at the ends and at bottom face of mid length. Now let's understand the ductile detailing code prescriptions for longitudinal bars. As you can see in this figure 3, at least 2 bars must go through the full length of beam at top as well as bottom of beam. Secondly, at the ends of the beam, means at the support, the amount of steel provided at bottom should be at least half than that at top. Now let's understand the role of stirrups or closed steel loops through this figure 4. Stirrups help in 3 ways. First of all, they carry the vertical shear force and thereby resist diagonal shear cracks. They protect the concrete from bulging outwards due to flexure or bending, and they also prevent the buckling of compressed longitudinal bars due to flexure or bending. Again, the ductile detailing code IS 13920 prescribes 3 requirements for stirrups in moderate to severe seismic zones. First, the diameter of a stirrup must be 6 mm, and in beams more than 5 meter long, it must be 8 mm. As you can see in this figure, the ends of vertical stirrups should be bent into 135-degree hook and should be extended sufficiently beyond this hook so as to ensure that stirrup does not open out in an earthquake. Also, spacing of vertical stirrup in any portion of the beam should be calculated through design. Now let's look at this figure 5, which shows the maximum spacing of stirrups. As per 13920, maximum spacing of stirrup is less than half the depth of beam, let's say D. Further, this figure shows for a length twice the depth of beam, that is 2D, from the face of the column, even denser spacing of stirrup is required, namely half the spacing mentioned for mid-length. In simple language, it means stirrups at ship support should be spaced closely, and the spacing should increase as we move toward the center of the beam along its length. Now let's discuss lapping of reinforcement through this figure 6. Steel reinforcement bars are normally available in length of 12 to 14 meter. Thus, it becomes necessary to overlap bars when beams of longer lengths are to be constructed. Remember, at the location of lap, the bar transfers larger forces from one to another. Therefore, the ductile detailing code, that is IS 13920, prescribes that such laps of longitudinal bars as shown in this figure are made away from the face of column, not made at locations where they are likely to stretch by large amounts and yield, that means bottom bars at mid-length of beam. Also, at the location of lap, vertical stirrups should be provided at closer spacing as shown in this figure. This is all about earthquake tip number 18. You can download this earthquake tip from www.bmtpc.org. The next earthquake tip, that is tip number 19, will be on how do columns in RC buildings resist earthquakes. Thank you.